how SpaceX's Mechazilla works. At Starbase in Texas, SpaceX has a towering rocket-catching mechanism called Mechazilla that is intended to transform rocket recovery by catching the super-heavy booster in midair as it descends. Utilizing sophisticated sensors and real-time control systems, Mechazilla's two enormous robotic arms, dubbed chopsticks, precisely track and capture the rocket, reducing wear and tear and facilitating quick reuse. This creative method improves the efficiency and sustainability of space travel by drastically cutting turnaround time and launch expenses. The following is a brief 7-point guide to SpaceX's Mechazilla. Number 7. Launch and ascent. SpaceX's Starship system launch sequence, which starts at the company's Starbase facility in Boca Chica, Texas, is a wonder of contemporary aerospace engineering. The Super Heavy booster and the Starship upper stage are stacked on top of each other to form the fully integrated vehicle, which is about 120 meters tall. A powerful array of 33 Raptor engines, each propelled by cryogenic liquid methane and liquid oxygen propellants, powers the Super Heavy booster. Together, these engines provide over 15 million pounds of thrust, making it the most potent booster ever built. The enormous rocket is lifted off the pad with tremendous force at liftoff when all of the engines ignite at once in a meticulously planned sequence. The structure is subjected to strong aerodynamic forces as the vehicle ascends through the dense lower atmosphere and reaches max Q, the point of maximum dynamic pressure. Engine throttling and gimbal angles are adjusted to preserve maximum stability and efficiency during this period by onboard avionics and flight computers, which continuously monitor engine performance, structural loads, vibrations, and trajectory data. In order to provide a smooth and controlled ascent, the booster's job is to precisely control pitch, yaw, and roll while delivering the overwhelming power required to launch the Starship upper stage toward orbital velocity. Number 6. Booster separation. The booster starts the complex process of stage separation about 159 seconds into the flight, at a height of about 64 kilometers. To preserve stability and attitude control, the Super Heavy booster throttles down the majority of its engines while keeping a few running. In the meantime, in a procedure known as hot staging, the top stage of the Starship starts its own Raptor engines, while it is still connected to the booster. By eliminating the requirement for coasting time and enabling a smooth thrust transition, this novel technology increases staging event efficiency while using less fuel. The physical link between the two stages is released by mechanical and pneumatic mechanisms after the upper stage reaches full thrust, enabling a clean separation of the booster in order to orient its engines downward for re-entry and landing. The rocket performs a complicated 180-degree flip maneuver as soon as it separates, employing its grid fins and cold gas thrusters. While the Starship upper stage continues its orbital journey, this movement is essential for positioning the booster to safely return to the launch site. This sequence's timing and accuracy are essential for reducing velocity loss and guaranteeing the booster's controlled descent trajectory. Number 5. Controlled descent of the booster. After separation, the Super Heavy rocket begins its controlled descent back to Earth, which is an extremely demanding and complex flying phase. The booster cancels its forward velocity and reverses its trajectory toward the launch site by performing a boost backburn, which involves rekindling several Raptor engines, usually 10 or more, in order to maximize fuel consumption and guarantee that the booster's trajectory would overlap the landing tower. This burn necessitates exact engine thrust and burn time calculations. The booster uses grid fins, which are big, foldable aerodynamic surfaces positioned close to the top, to generate lift and drag forces during descent, giving it precise control over its attitude and direction. In order to steady the vehicle against atmospheric disturbances including wind shear, turbulence, and gusts, cold gas thrusters also offer quick attitude corrections. Onboard sensors and tracking systems on the ground continuously monitor the booster's descending path to make sure it stays on plan. The booster must perform a precise landing approach on the Mechazilla-equipped launch tower, which requires complex flight control algorithms that include real-time data to dynamically modify engine throttle, fin angles, and thruster firings. Number 4. Real-time tracking and positioning of Mechazilla arms. The Mechazilla system, a giant launch and recovery structure around 150 meters tall, deploys its 2 enormous robotic arms, each known as chopsticks, when the rocket approaches the landing site at hypersonic speeds. These arms are powered by sophisticated hydraulic actuators that can exert forces more than 1,000 kilonewtons per arm and are constructed from ultra-high-strength steel alloys. The arms are equipped with a variety of cutting-edge sensors, such as LiDAR scanners, infrared imaging systems, and high-resolution optical cameras, which continuously record precise velocity and location data of the descending booster. High-performance onboard and ground-based computers use this sensor data to feed complex machine learning algorithms and predictive control software. Number 3. Catching the booster midair. Mechazilla's robotic arms close in with amazing speed and accuracy to seize the booster's aft part as it decelerates to almost zero velocity just above the launch mount. In order to attach the booster without applying harmful stresses, the grippers on the arms are constructed with a combination of mechanical locking mechanisms and pneumatic cushions that absorb residual kinetic energy. In contrast to conventional vertical landings on pads or drone ships, which expose the booster to hard impact, pressures that may result in structural stress and necessitate significant renovation. Number 2. Placing the booster back on the launch mount. Once the launcher is safely grasped, Mechazilla's robotic arms meticulously move to precisely reposition the booster on the launch mount. To prevent any lateral forces that would destabilize the booster or harm the launch infrastructure, the arms must carefully coordinate their movements during this process. The placement streamlines the entire recovery procedure by doing away with the requirement for cranes or other ground handling equipment that are typically used to collect and transport rocket stages. According to Elon Musk, the boosters that Mechazilla grabbed and installed. Number 1. Rapid reusability and turnaround. Mechazilla's main objective is to revolutionize rocket recovery and reuse by facilitating the super heavy booster's quick turnaround, which will significantly cut down on launch time and cost. SpaceX avoids the damage and delays that come with conventional landings and ground handling by grabbing the rocket in midair and putting it straight onto the launch mount. The ambitious goal of getting boosters ready for reflight within 1 hour of landing, a groundbreaking standard in aerospace history, has been openly expressed by Elon Musk. After stage separation, the booster usually takes 5 minutes to descend and recover. The remaining time is spent on quick inspection, small repairs, fueling, and integrating with the top stage of the Starship. SpaceX's goal of frequent, affordable launches that can satisfy the requirements of satellite constellations, interplanetary missions, and quick access to space is supported by this capability. In order to make spaceflight more sustainable, regular, and accessible, and to open the door for human expansion throughout the solar system, Mechazilla significantly improves reusability and operational cadence. In conclusion, the 400-foot-tall Mechazilla is equipped with 2 enormous mechanical arms that are intended to capture the super heavy booster in midair as it descends. Accurate tracking and control systems are used to facilitate a rapid, effective, and reusable rocket recovery. This development represents a significant advancement in the efficiency of space missions and reusable rocket technology. If you liked our video, please hit the like button and subscribe to our YouTube channel.